Hello, viewers. Welcoming all viewers to the session on stack data structure. Okay, let's look into the stack data structure, a fundamental concept in computer science and programming. Understanding how stacks work and their key characteristics is essential for efficient algorithm design and problem solving. Let's look into the details of the stack data structure that focus on its definition and the last in, first out principle. So, what is a stack? A stack is a linear data structure that organizes elements in a sequential manner, similar to a stack of plates or books. So, what distinguishes a stack from other data structures is its adherence to the last in, first out principle, LIFO principle. This means that the last element added to the stack is the first one to be removed. Stack operates on two primary operations named as push and pop. Elements are pushed onto the stack from one end, called the top, and popped off the stack from the same end. The last in, first out principle governs the behavior of stacks, dictating the order in which elements are added and removed. When a new element is pushed onto the stack, it becomes the new top element, effectively covering the previously added elements. Consequently, the last element pushed onto the stack is the first one to be popped off, allowing for efficient access to the most recently added elements. This property makes stacks ideal for managing function calls, tracking the state changes, implementing undo operations in software applications. The push operation adds a new element to the top of the stack, increasing its size by 1. Conversely, the pop operation removes the top element from the stack, reducing its size by 1. These operations maintain the integrity of the stack's LIFO behavior, ensuring that elements are added and removed in the correct order. Additionally, stacks typically support other operations such as peek, which allows for viewing the top element without removing it, and isEmpty, which checks if the stack is empty. So on the whole, the stack data structure follows LIFO principle and consists of elements organized in sequential manner. By understanding how stacks operate and their key characteristics, programmers can understand this data structure effectively in various applications, including expression evaluation or backtracking algorithms and managing function calls in software development. The fundamental operations performed on stack are push, pop, and peek. These operations are essential for manipulating and accessing data within a stack data structure. Understanding how each operation works is very important for efficient stack manipulation and algorithm design. The push operation is used to add a new element onto the top of the stack. When we push an element onto the stack, it becomes the new top element, covering the previously added elements. This operation increases the size of the stack by 1. The push operation is fundamental for building up the stack with new elements, allowing us to store data in a sequential manner. In programming, pushing elements onto the stack is commonly used for implementing algorithms like DFS, depth first search, and expression evaluation. The pop operation is used to remove the top element from the stack. When we pop out an element from the stack, it is removed from the top, reducing the size of the stack by 1 again. The element that was popped off the stack is returned or used by the program. The pop operation is essential for accessing and removing elements from the stack in the reverse order they've been added. So it follows the last and first out principle, ensuring that the most recently added element is the first one to be removed. Pop operations are frequently used in algorithms that involve backtracking, such as DFS, depth first search, or undo functionalities in text editors. The peek operation allows us to view the top element of the stack without removing it. That need to be understood clearly. Like the pop operation, which removes the top element from the stack, the peek operation only retrieves the top element without modifying the stack's size or contents. Peeking at the stack is useful for inspecting the next element to be processed or for performing conditional operations based on the top element's value. It provides a way to access data without altering the stack's state, making it a valuable tool in algorithm design and implementation. In summary, the push, pop, and peek operations are fundamental for manipulating stack data structure. Pushing adds a new element onto the stack, popping removes elements from the top, and peeking allows for viewing the top element without removal. By mastering these operations, programmers can effectively manage and utilize stacks in various algorithms and applications. So let's look into the diverse and practical uses of stack in software development. Stacks are versatile data structures that find application in various algorithms and functionalities across different domains. So understanding these applications is essential for leveraging stacks effectively in programming and problem solving. One of the main or the primary uses of stacks in software development is managing function calls during program execution. Each time a function is called, its execution context, including parameters, local variables, and return address, is pushed onto the stack. As the function completes execution, its context is popped off the stack, allowing the program to return to the caller. This mechanism, known as the function call stack, enables recursive function calls, nested function invocations, and efficient memory management during program execution. Stacks are instrumental in evaluating mathematical expressions, particularly infix, postfix, and prefix notations. During expression evaluation, operands and operators are pushed onto the stack, and operations are performed based on their precedence and associativity. Stacks facilitate the systematic processing of expressions, ensuring proper order of operations and precedence handling. Additionally, stacks are used to convert between different expression notations such as infix to postfix, making expression evaluation algorithms more efficient and versatile. Backtracking algorithms rely heavily on stacks to explore and backtrack through solution spaces efficiently. In algorithms like DFS and backtracking search, a stack is used to maintain the state of the search process, including the current path and the decision points. As the algorithm explores different paths or choices or states are pushed onto the stack, and if a dead end or invalid solution is encountered, the algorithm backtracks by popping states off the stack and exploring alternative paths. This recursive exploration and backtracking process enable efficient search and solution finding in various combinatorial and optimization problems. Now, stacks are employed in implementing undo mechanisms in software applications. allowing users to revert changes and restore previous states. Each action or modifications performed by the user is recorded as a command or operation, which is pushed on to the undo stack. If the user decides to undo an action, the corresponding command is popped off the undo stack and executed in reverse, effectively reverting the change. So stacks provide a straightforward and efficient way to manage the history of user actions and facilitate undo functionality in applications ranging from text editors to graphic design softwares. So stacks have numerous practical applications in software development, including managing function calls, evaluating expressions, as I discussed earlier, backtracking algorithms, implementing undo mechanisms, etc. So understanding and leveraging these uses, programmers can understand the power of stacks to solve complex problems and build robust and efficient software solutions. Now, array implementation and linked list implementation. Let's understand how stacks can be implemented using these data structures. And this understanding is crucial for building efficient and versatile stack-based algorithms in C. The array implementation of a stack involves using a fixed size array to store stack elements. The array represents the stack's underlying data structure with elements arranged sequentially. Key points to be noted here is that the array size. The size of the array determines the maximum capacity of the stack. It should be chosen carefully based on the expected number of elements and memory constraints. Next is a pointer, typically called a top pointer, which is used to keep track of the top element of the stack within the array. Initially, the top pointer is set to -1 to indicate an empty stack. When pushing an element onto the stack, the top pointer is incremented, and the new element is inserted into the array at the position indicated by the top pointer. When popping an element from the stack, the top element is removed from the array and the top pointer is decremented to point to the next element in the stack. The linked list implementation of a stack utilizes a dynamic data structure called a linked list to store stack elements. Unlike arrays, linked lists can dynamically adjust their size, making them suitable for implementing dynamic stacks. Key points to note about linked list implementations are each node it's about the node structure in the linked list. That is, each node in the linked list contains two components, the data field to store the stack element and a pointer to the next node in the list. The next element to be noted keenly is the top pointer. Similar to the array implementation, a top pointer in the linked list is used to keep track of the top element of the stack. In the case of the linked list, the top pointer points to the first node of the list. And when pushing an element onto the stack, a new node is dynamically allocated. And the top pointer is updated to point to the newly created node. The element is then inserted into the node's data field. When popping an element from the stack, the top node is removed from the list and its data field is returned. The top pointer is then updated to point to the next node in the list. So on the whole, both array as well as the linked list implementation offer unique advantages in terms of memory usage, flexibility, and performance. So understanding these implementations allows programmers to choose the most suitable approach based on the requirements of their specific application. So this is how the array is being implemented, a short program that demonstrates and shows you how the program or array is being implemented. Now let's here, if you look into the program, I've created a constant 100 and I've used hash define to name it as maximum size. So here that I've declared an array in the name of stack. Its data type is integer and the size of the stack is the maximum size. I've declared a variable called top and of integer type. Initialize this to -1. So here there are two functions, a push and a pop. The return type of push is void and it takes a parameter named element of integer type. So if the top is greater than or equal to the maximum size -1, the program prints stack overflow and returns, or else it pushes that element into the array called stack and then increments the top element. Rather, it increments the top element, thereby top will point to a new space to which the element is being assigned. The value stored in the element is assigned to the place where top is pointing to in the array. In the case of popping function, we are checking whether the top is less than 0. In case the top pointer value is less than 0, it's understood that the stack is underflowing and the program returns -1. Otherwise, if it is not less than 0, it means that the stack has got values. So we are removing the top element or the value that is pointed to by the top. After it has been removed, the top is being decremented. The same is the case with the linked list here. Now we're making use of structure here. We're creating a new structure in the name of node consisting of two elements. One is the data element of integer type. Another one is a pointer named next, which is of the structure type itself. So it has been specified as struct node star next. Now that I declare a pointer named top, which is of struct type, and I'm initializing that to here we have push and pop functions. Hope it's visible. I'm trying to push an element here. So defining a function named push whose return type is void, and it takes a parameter of integer type named element, inside which I'm creating a new node of the structure type and I'm dynamically allocating memory. After the memory has been dynamically allocated, I accept value or the value inside the element has been assigned to the structure element called data and has been accessed using the new pointer that has been created using the structure. Once if the data has been given the value, the next part of the data is equal to assigned to top, which is actually null here. Now we say top is equal to new node because this is the very first head node for the list. This slide talks about time complexity analysis of array and linked list implementations, focusing on the push and pop operations. Understanding the time complexity of these operations is crucial for assessing the efficiency and performance of stack implementation in both data structures. Time complexity in array implementation. In the array implementation, of a stack, both the push and pop operations have time complexity of O of 1, which means a constant time. This means that regardless of the size of the stack, the time taken to perform these operations remain constant. So a key point to be noted here is that time complexity in array implementation includes adding an element to the top of the stack in an array. Array implementation involves assessing the next available index in the array and inserting the element. Since the array size is fixed, accessing and updating the top of the stack can be done in constant time, resulting in O of 1, which is a constant time complexity. Removing an element from the top of the stack in an array implementation also involves accessing the top element's index and removing it from the array. Similar to the push operation, this process can be done in a constant time, so it is represented as O of 1 time complexity. Time complexity in the case of a linked list implementation. Both the push and pop operation also have time complexity of O of 1, which is a constant time. Despite the dynamic nature of linked list, these operations remain efficient due to the structure of the linked list. So a point to be noted here is that time complexity in linked list for pushing operation is adding an element to the top of the stack in a linked list implementation involves creating a new node and updating the top pointer to point to this new node. Since linked lists support dynamic insertion, updation of pointers, this process can be done in a constant time. In the case of popping, Removing an element from the top of the stack in a linked list involves updating the top pointer to point to the next node in the list. So the time complexity here also is constant. So this constant time complexity ensures efficient stack manipulation regardless of the size of the stack, making them suitable choice for various applications in software development. So let's compare two popular data structures, array and linked list, examining their strength, weakness, and common use case. So understanding the difference between these structures is important for making decisions when designing algorithms and selecting appropriate data structure for particular tasks. So arrays are a fundamental data structure in programming, offering contiguous memory allocation for storing elements of the same data type. So the key characteristics are fixed size, which means arrays have fixed size determined at compile time, and the size cannot be changed dynamically during programming. And arrays support constant time access to elements based on their indices, so allowing efficient retrieval and manipulation. Now, arrays also offer excellent memory efficiency as they require a single block of contiguous memory to store elements. In the case of linked lists are dynamic data structures that consist of nodes connected by pointers, allowing dynamic memory allocation and flexible size adjustments. Key characteristics of linked lists are dynamic size because they grow and shrink dynamically during program execution, making them suitable for cases where size of the data structure is unpredictable. And linked lists require sequential traversal from head till the tail to access elements, which may be a little slower as compared to arrays. Linked lists incur additional memory overhead because due to shortage of storage of pointers for linking nodes, which can impact memory efficiency as compared to arrays. So let's compare arrays and linked lists in few criterias. Arrays offer constant time access to elements, while linked list requires sequential traversal from the head, so resulting in O of n access time in the worst case, that is linear. Linked lists excel at insertion and deletion operations, which can be done in constant time by updating pointers. Arrays, on the other hand, may require shifting elements to accommodate insertions or deletions, resulting in linear time complexity. So arrays typically offer better memory efficiency due to contiguous memory allocation, while linked lists may incur higher memory overhead due to pointer storage. So arrays and linked lists offer distinct advantages and trade-offs in terms of access time, insertion, deletion, efficiency, and memory usage. So choosing between these structures depend on um, the specific requirements and constraints of the application, with arrays being suitable for cases requiring random access and memory efficiency, whereas linked lists are preferred for dynamic size adjustments and efficient insertion deletion operations. So, having compared two popular data structures, arrays and linked lists, examining their strength and weaknesses and common use cases, understanding the difference between these structures is crucial for making decisions when designing algorithms and selecting appropriate data structures. Arrays are fundamental data structure in programming, offering contiguous memory allocation for storing elements of the same data. And arrays have fixed size determined at compile time. All these we have discussed in the previous slides. So arrays support constant time access to element based on their indices, and it offers excellent memory efficiency as they require a single block. A linked list, as we discussed earlier, it is a dynamic data structure that consists of nodes connected by pointers, allowing for dynamic memory allocation and flexible size adjustments. And linked lists require sequential travel from the head to the access elements. So linked lists incur additional memory overhead due to storage of pointers. So as we discussed earlier, access arrays and linked list uh, takes the time complexity is constant in insertion and deletion. So arrays and linked lists offer distinct advantages in terms of access time, insertion, and deletion. And linked lists are preferred for dynamic size adjustments and efficient insertion and deletion operations. So in our conclusion on fundamental data structures, it is essential to reflect on the key takeaways and implications. So we have explored various data structures, their implementations and practical applications, highlighting the importance of mastering these